right, good afternoon. My name is Riley Edwards, and I want to welcome everyone to our William W. Hay Railroad Engineering Seminar. Before I introduce our speaker today, I want to take care of a few housekeeping items. First of all, if you have a cell phone, please silence it for our seminar. Secondly, if we happen to have a fire alarm, please exit from either set of doors, go down the nearby stairwell, and then we will gather across the street on the north side of Main Street by the Civil and Environmental Engineering Building. And we ask to use the buddy system, so note who is beside of you so we make sure that we all get out safe and sound. If you didn't swipe your ID earlier, please let us know and we can jot your name down and make sure that you're on our seminar distribution list. And one request of the speaker, if you can repeat the questions, especially if they come from up front, if you repeat them back into the microphone so everybody online hears the questions. So one very special announcement I have today. Prior to starting the Hay seminar, Professor Barkan's not in the room with us today, but we kind of feel like it because of the size of the image here on the screen. But I wanted to make special acknowledgement of a really exciting award that was recently given to Professor Chris Barkan. He was awarded the Robert E. Skinner Jr. Award. This award comes from the Transportation Research Board, as you can see, and it's a Distinguished Transportation Research Management Award that recognizes outstanding achievement in management, administration, promotion, fostering, and implementation of transportation research. So the award honors Robert Skinner, who served TRB for more than 30 years, including as its executive director. And personally, and I think collectively for the Railtech team, we couldn't be more excited to see Chris given this deserving award. It's in recognition of nearly 4 decades of his contributions to rail engineering. And I think, again, those of us that are here in the room and online know how much Chris has impacted the railway industry and that we wouldn't be here in this form in Railtech without Chris. So the award will be formally conferred to him in January at the TRB annual meeting. But for now, congratulations, Chris, and maybe a round of hands. So especially to some of the new folks, and we're so excited, we have 400 people registered online. So I know there's some new folks that have not participated in prior Hay seminars. So I'm going to give a little bit of background on the Hay seminar series and how we got to where we are today. So the William W. Hay Railroad Engineering Seminar Series is sponsored by the Rail Transportation and Engineering Center here. We host it, we sponsor it, but we also want to thank all of the contributors to Railtech, including the Association of American Railroads, Canadian National, the BNSF Railway, and the National University Rail Center of Excellence, along with Hanson Professional Services. These are entities that have been longtime supporters of Railtech, and we sincerely appreciate their contribution. Today, I want to make special recognition of the support from BNSF. The support that Railtech has obtained from BNSF began way back in the 1990s when Chris started his now 27 or 28-year tenure here. And there was a great relationship between the TR&D group in Topeka, and then eventually in the system engineering group down in Fort Worth that has spawned a lot of growth of Railtech and some really fruitful collaborations in the field. So we're grateful for that and seeing those relationships to continue even through our speaker today. So we look forward to further deepening those relationships and staying in good communication. As I mentioned earlier, we have about 400 people online, and these individuals represent engineering consulting firms, railroads, universities, research organizations, technology developers, etc. And to the folks online and the folks in the room, we're really grateful that each of you are able to join us today. If you would like a PDH and you didn't already get to sign up, please follow the instruction either in the email or see Chrissy and Emma here in the room today. Now to introduce today's speaker and topic, I'll start by describing, at least in brief, what our speaker today will be discussing. So the BNSF Railways System Maintenance and Planning Organization is responsible for the measurement, testing, and capital planning of 28,000 miles of BNSF track. Over the past 25 years, BNSF's technology and process improvements have steadily reduced the rates of derailments, most notably track-caused derailments. In recent years, BNSF's track maintenance and planning processes have become even more data-driven with increased track measurement testing platforms, including 2 of which that were developed in-house by BNSF. Their system maintenance and planning team continues to further expand and leverage data to improve track reliability and railroad service metrics. So now I'm honored to introduce our speaker today. I'm going to introduce Mr. Todd Kuhn from BNSF. Mr. Kuhn is the Assistant Vice President and Chief Engineer of System Maintenance and Planning at BNSF, where he serves in his role in Fort Worth, Texas. He has served in this role since June 2024, and he has system-wide responsibility at BNSF to drive advances in track maintenance efficiency and productivity across their engineering department. Since joining BNSF in 2006, Mr. Kuhn has had many roles in engineering with increasing responsibility. He served as a division engineer, director of engineering services, director of engineering certification, director of engineering safety, and general director of maintenance, also general director of maintenance planning. Mr. Kuhn received his BS degree in civil engineering from Penn State University, and there's some great people there. We acknowledge that in this room, and is a licensed professional engineer. He's originally from Alexandria, Virginia, and now he lives in Trophy Club, Texas with his wife, Carrie, and their children. So please join me in welcoming Mr. Todd Kuhn, who will present today's seminar titled Database Track Maintenance and Planning at the BNSF Railway.
Well, thank you, Dr. Edwards, for the introduction, and glad to be here today, and certainly appreciate the invite from RailTech and Dr. Edwards to speak here today. Certainly an honor, and we too at BNSF also appreciate the collaboration and partnership we have with RailTech also. So, as he mentioned, name's Todd Kuhn, Chief Engineer with BNSF out of Fort Worth, Texas. I work in our engineering department. And here today, I'm going to talk about database track maintenance and planning. So we'll start off with really what I think most of you are familiar with BNSF Railway here, but just to kind of give you a reminder of who we are. So our network is across the western 28 states, our route miles, over 32,000 route miles. And when it comes to what we maintain as an engineering department, that encompasses about 28,500 main track miles, almost 10,000 other than main track miles, which are sidings, yard tracks, other types of back tracks, and then quite a few bridges and tunnels, and we serve lots of ports and intermodal facilities. So pretty large network. And as I'm going to talk about today, you know, data is a big piece of what we do at BNSF. And so within the engineering department, obviously an engineering department at BNSF, we maintain all of our infrastructure. When you think about the track and the bridges and the signal system, tunnels, of course, any structures out there. So we're responsible for the infrastructure. So what my team does, so we're called the System Maintenance and Planning Team, which I have responsibility for. So you think about what really that is. It's lots of different things. I mean, we have the teams in the field, our field teams that do the day-to-day maintenance in the field. But my team's responsibility is for really everything you see on this slide that goes up here. I mean, first and foremost, we're all about preventing derailments, keeping the wheels on the rail. And many of the things you see up here on this slide contribute to that. But we're all about derailment prevention initiatives. And you can think, I'll highlight a few others on here. Anything related to rail, it falls under my team. When it comes to rail detection, rail grinding, you know, rail procurement and delivery, rail welding in our rail plants, rail lubrication. And then of course, track measurement is one of the big things I'll talk about today. Track measurement is really what generates all of our data that feeds a lot of the things that we do as part of our system maintenance and planning team. And then the other big piece that I have is capital planning and really the capital budgeting and estimating that goes into maintaining a railroad. So typically this year and next year, BNSF will spend approximately $1.5 billion in track maintenance. So, and those are the things we plan. You think about $1.5 billion of work, that's billion with a B. That certainly takes a lot of effort to plan all the things that go into that, and data is a big piece of that here. So I'll get into some of that of what we do. Now, certainly I'm not going to have time to talk about all these things on here, but I'm going to focus on the bigger items in the time we have that really involve track measurement and capital planning and how those all work together in terms of how we use data to do that. So I can't really talk about anything at BNSF without starting with safety first, because when you think about it, our values at BNSF are really closely aligned with the values of anyone that's in the engineering profession. If you think about anyone in here that's an engineer, I'm a civil engineer. I graduated as a civil engineer from Penn State and really and professional engineer. But any engineering discipline that you go into, you think about whether you call it the engineer's creed or the engineer's vision or the engineer's mission. Usually it revolves something around the engineer's duty is to make sure that the public health, safety, and welfare is protected, and your mission as an engineer is to make sure that that is first and foremost in everything that you do. Same holds true working at BNSF. Safety is first and foremost, and we often say that safety is a value at BNSF. Values don't change, priorities do over time, and safety is one of our core values that's part of everything that we do. So we're proud to say that in terms of our train accident safety, we are the leader in the industry, and you can see on here where we've been the leader for the last 9 years. And I put train accidents up here specifically because that, as an engineering department, system maintenance, and planning team, this is what we're trying to prevent. We're trying to keep trains on the rail and from derailing. And you can see BNSF has had a very, very strong record in this, and we've reduced total train accidents by 63% since the year 2000. Now, I'll dive into that a little bit deeper because train accidents have multiple different causes, right? They're not all caused by track. There's lots of different causes. And one thing that maybe doesn't have that much visibility is what goes into what we categorize as a train accident. You can see the largest factor is something that's human caused, whether it's human error or not following the rules. But what we focus on my team in terms of track maintenance and planning is this piece down here. Is anything that is track or signal related makes up about 1/4 of all train accidents on our network. So we are very focused on driving these down in all of our processes here. And good news in here showing this is our engineering reportable REIs. So you may hear me talk about REI. That stands for Rail Equipment Incident. And really that's a train accident as a larger scale that involves something on the rail that has an incident. Now, most of it, as you think about, when we think about it in a normal term, we talk about is a derailment. So when a piece of rail equipment, usually a train, leaves the rail and hits the ground, that is what we're always trying to prevent within engineering. And looking back here over the last 25 years, I mean, it's a very nice trend downward. And on the other slide, it mentioned that we've reduced total train accidents by 63% over the last 25 years. When you look at just engineering caused derailments, which are typically track and signal is the large piece of that, that we've reduced those. We're on track to reduce those by close to 72% over that same time frame. So 2025 year end, we're not quite there yet, but it's shaping up right now to be our lowest rate of track related derailments this year, which is certainly what we're all about and keeping that trend line going. But really what this goes to show is it's really the opposite of maybe the narrative that we see out there on the news or social media, but the number of train accidents, derailments, reportable incidents, specifically track caused ones, are steadily continuing downward. And the key things that are driving that are really what's on the screen here today. I won't read every single one, but it's all the technology and safety and process improvements that we've made over the years. And this certainly isn't everything by all means, but these are the biggest things that, in my opinion, have influenced this downward trend over that time frame. When you think going back to just preventative grinding years ago, when we started that, better rail detection technology over that time frame. And what I'm going to focus most on here with our time today is really the last 10 years. If you look back starting at around the 2015 time frame, that's number 9 up there, is our unattended geometry car testing fleet and our geometry desk. which I'll talk about in more detail. So it's been about 10 years, and you can see we've had quite a bit of process improvements that have resulted in that. But I would say that's really the milestone that I look back on this chart of 10 years ago. We started doing unattended geometry testing. So that's using our geometry cars out there with nobody on them that test our track. But that data is what feeds everything downstream of what we do and everything that we've developed since then. And certainly that has helped continue this steady line down here. And I'll talk about several of these other things here, but that type of geometry testing has led to other things like automated track inspection, which I'll talk about more. Our Thor system has developed from that too. And then most recently here, our Odin system here, which I'll get into a little bit more detail, which is our locomotive-based geometry testing platform as well. So certainly a good news story. And as an engineering department, we're not satisfied until this graph gets down to zero, which it will someday. But I think it's clear that all of these technology and process improvements, which we continue to build upon as we go forward, are what's going to help us bring this down to zero over time. So certainly we're proud of the progress that we've made. And just to put a little bit in perspective, sometimes when we talk about rates and numbers, it kind of loses its meaning a little bit. So I was thinking about how to better represent this and what this really means. So we measure engineering reportable rail equipment rate per million train miles. So that's measured of, this year we'll finish at 0.3 incidents per million train miles. So you think about that, that's about 1 per 3 million train miles, right? And what does that really mean? Well, I was thinking our main transcontinental route goes from Chicago to Los Angeles. Give or take, it's about 2,000 miles. So for a train to go, say a train just went back and forth, all from Chicago to LA, it would take, I was doing the math on this, if even our fastest train takes 2 days to get from Chicago to Los Angeles. And if you do the math, someone can check me on this. It's not good to do math in public, of course, but if you do that, it ends up being like, I think it's like 10 years or something like that we would go without a track-related derailment or reportable type incident. So that's what we're talking about, is something is going 10 years of a continuous route between Chicago and Los Angeles before we'd have one. Now, obviously, that happens more often because we have more than one train, but that's just to give you an idea of how often that these events happen. And the good news is it's not very often anymore. So I talked about 10 years ago is when we started our unattended geometry systems. And I'll get more into detail of what I mean when I highlight what we have. So these are our current track measurement platforms that we have today at BNSF. And I start with these because these really form the foundation of all the data that we generate. Not all, but I would say the majority of the data that we generate comes off of these platforms, with a few exceptions. So shown there on the upper left, so we continue to have we call two attended geometry cars. So that means there's people on those cars operating them, physical people on those cars, making sure they're running properly. So those cars generate track geometry. And when we talk about track geometry in the industry, we're generally referring to gauge, surface, and alignment. So measuring the gauge, distance between the rails, the surface of the track, and then the alignment of the track as well. Those systems also have Thor. So I'll get into more about what Thor is, but it's our optical recognition system. They also have LiDAR, so laser scanning. We scan the entire right of way with LiDARs on those cars. And then ground penetrating radar. We look down into the ballast section with radar to detect the quality of the ballast section, the amount of moisture in the ballast section, the amount of fouling in the ballast section as well. So those are the platforms that have the most, I would say, technology on them in terms of like the amount of things we're measuring. And those are things I would categorize this as we try to get across our network at least once a year with those cars, meaning anywhere on our network, you think about, we want to get that consist across it about once a year at a minimum. We're not really looking to test that like every week, every couple weeks, because we don't need to run ground penetrating radar that often. We don't need to run LiDAR that often. But that's why we have our unattended cars and the locomotive platforms. So our unattended cars, I mentioned, we released those in 2015. So those have been around for about 10 years. We started with 2, we're up to 4 currently. So that's basically a car. It's on the lower left there, but there's nobody on it. It's just it's locomotives pulling that car, and there's nobody on there. It's completely remotely operated from our geometry desk in Fort Worth. So that is looking at track geometry, and then a few of those cars also do have what we call our remote Thor system on there. So it's the same optical system. There's just nobody on the car running it. And those are the cars we want to really cycle quickly. Those operate 24/7 versus the attended cars are operating really during business hours. Those unattended cars, we keep cycling all the time to get as much railroad covered as possible. And that's where we generate most of our testing miles, is from those unattended cars. Now, we're currently in a transition phase right now where we now have revenue service locomotive geometry testing. So we currently have 23 revenue service locomotives with a geometry testing system on it, which we refer to at BNSF called Odin, which I'll get to in more detail here in a second. But that is the same thing that's on a geometry car is now underneath the locomotive, of which we have 23 of those. And we're transitioning now to do more revenue surface testing with locomotives than with our unattended geometry cars. So that's one change we've made here this year. We also have 65 VTI systems, so that's vehicle track interaction systems. Those are accelerometers on the locomotive that measure the acceleration both in the vertical and horizontal direction. Also is another way to detect potential track anomalies, is through the acceleration of the locomotive, whether it hits a hard spot or it comes across something that moves it in an unusual manner. And then lastly, we have 7 high rail trucks shown here on the right. There's a lot of locations on our network where testing via rail car is not practical. It might be around terminals where it's hard to get a train through, in a terminal, branch lines that are single-ended where it's tough to get a train up and back without having to swap power and crews and all that business. So we also have high rails that supplement the areas of the system that we can't test easily with a rail-bound platform. So the things I want to focus on the most are I would say the items that we're the most proud of at BNSF, because these have all been homegrown projects of ours that we've done all in-house. And I would say all of these have been a collaboration between the engineering department where I work and also TR&D, which is our technical research and development group in Topeka, Kansas, have designed and built a lot of this along with us, in addition to our technology services department as well, which has helped with a lot of the technology that makes all these systems work here. But these 3 items here that I show are really the foundation of our track measurement system. So Odin, I mentioned, is the newest platform we have. So that's stands for onboard defect identification and notification. So that is 100% BNSF designed and built. It was not, we didn't outsource it, buy it from any kind of outside company. It was completely designed by our TR&D group in Topeka, like I mentioned. And we're certainly proud of that, built from the ground up. So everything that's gone into that, we've done ourselves, and we've been part of that for the last 3 years. And very proud that we did in-service it into revenue service testing earlier this year. So this is our first year running Odin units in revenue service. So that is a big milestone that we're certainly proud of here at BNSF. And we currently have 23 units out there, and our plan is to continue with more of those. We're hoping to have over 30 by the end of this year, and ultimately looking to put out about 65 out there on the railroad. And that's something where I'll say, frankly, we probably don't know the right number on exactly how many we need. Certainly, there's a point of diminishing returns when you talk about testing that I'll probably talk about a little bit more. Is there's a point where you probably can test too much, and where you can keep testing and keep testing and keep testing, but you're really not gaining anything by testing more. So Thor is the other side of it. So Odin, you think about as a laser-based geometry system. It's testing track geometry, so gauge, surface, and alignment. So it's looking at the alignment and the geometry of the track and testing it up against both FRA and BNSF standards. Thor, on the other hand, is an optical system But just like Odin, it's 100% designed and built and maintained by BNSF completely in-house. So it is a line scan optical system. And I'm certainly going to give a lot of credit to TR&D and in Topeka again. They did most of the design and development of this. And it's an optical system. So it's taking pictures of the track, and it's machine-based learning that looks at what are things in the track that we want to know about and protect and correct, so that before something happens, whether it's a derailment or some other event. So good example here. That's picture on the top there is a joint bar. Clearly there's supposed to be a gap in the rail at the middle of the joint. This is supposed to be there. That's a joint. This is not supposed to be there. So that rail has broken. So for those of you that aren't that familiar with joint bars. And then even on this one, you might say, well, what's wrong with that? I don't even know what's wrong with that. But somewhere in here, there is a hairline crack that Thor identified that eventually is going to turn into a larger crack. But Thor is good enough to see those hairline cracks that I would say years ago, that hairline crack probably progressed and progressed and progressed and progressed. And maybe a track inspector saw it at the right time and was in the right place at the right time to find it. But more than likely, it eventually would break, and possibly it gets found, possibly it doesn't, possibly a train finds it, which is certainly what we don't want to happen. But I would say the biggest game changer of Thor, it's finding these things, but I'll mention in a second, it's finding these types of breaks that are really difficult for either a human or another system to find, because they're in challenging locations like this that have a lot of things going on, and Thor can really do a good job at picking out the exceptions. Last thing I'll mention, geometry desk is, I think, is fairly unique at a class 1 rarity, is we do have a fully staffed 24/7 geometry desk in our network operations center in Fort Worth. So that is these pictures right here are in our NOC, as we call it, right down where all the dispatchers sit in Fort Worth. And they are responsible for monitoring all these geometry systems 24/7. So there's defects coming in from those cars. They are sending them out to the field. And they're also, for anything that is, we would call multi-class drops. So if those of you that are familiar with a class speed system on the railroad, so class of track is what we talk about when we talk about what speed is a track good for. I think many of you are familiar with those terms. But anything that drops a track multi-class, meaning we're going from, say, 60-mile-an-hour track to 25-mile-an-hour track or below, we consider that a multi-class drop. So that is a critical exception, and the geometry desk will issue a slow order immediately to the train, immediately out there, before anyone even has time to go out there and take a look at it from the field. They are issuing a slow order to slow or stop those trains before it comes to that condition. So I would say that is a game changer, where we've likely prevented lots of incidents by proactively protecting those conditions before they're found by a train. So certainly something that we rely on heavily. Now, the other thing that the track geometry desk does is we're very sensitive to making sure we don't send folks in the field out finding, chasing bad data. And I would say that's something that anyone that's involved in data collection, we always need to be sensitive about too, is you don't want to, data is good, but we don't want to be making decisions based on bad data. So, I mean, inevitably, when you're out there testing in the real world under various conditions, various weather conditions, you think about the extreme heat we go through in the desert to the extreme cold we go through in Montana, our track measurement systems test in all those different environments. And we inevitably have data issues from those systems, whether it's, we have for reasons that sometimes the data flatlines. Sun interference is a common problem, where if the sun is at the right low angle, it interferes with the lasers. So we're not going to get good data there. There's obviously other things. We have spikes in the data and other various reasons. Snow is a big challenge with us, especially on the northern region in the winter, with all the snow flying around and all the snow that the train kicks up. You can imagine that we have trouble getting a good test through that. So those are things that our geometry desk in Fort Worth tries to filter out. Now, I think as time goes on, that's one thing that our automated algorithms are filtering out a lot more of this than we were even a year ago or 5 years ago. So that continues to improve. But I would say our desk is also the last line of check before we send something out in the field, because we really want to make sure that before we send something to the field for someone to put their boots on, get out in their truck, potentially drive somewhere in the dark in the middle of the night to go check on something, we want to make sure that we are sending them out there for something that is really important for them to find and protect. So, but I would say, data quality is something we continue to focus on, and really, I think this is something that there's still a lot of opportunity in, and it's things that you don't see it when you test things in a laboratory environment, but when you bring things out into the real world, it leads to a lot of these challenges. So all of this geometry testing, the other thing we're proud of at BNSF is our automated track inspection program. So all this geometry testing that we started back in 2015 has really led to what it unlocks for us as not just a railroad, but as a full industry, is automated track inspection. So looking back, I'll focus on the graph on the upper right first. So 2015, I mentioned, was the year we really started our large-scale unattended geometry testing. And you can see our what we call non-compliant exceptions per 100 miles, which is any condition in the track that the geometry system finds where we have to drop the speed by at least one class. So those are the rate of those at that time. It was brand new technology at the time. Before that, a track was probably receiving a geometry test on average maybe 3 times a year at that time. And then once we ramp that up, you can see what happens to our exception rate. It just nosedives, and which tells us we found that the more you test, the better the track does, because people know the condition of the track. They can see the change in the track. And at that point, we were probably getting geometry tests once a month compared to 3 times a year. And very quickly, we saw the condition of our track improve, just because people had better visibility of the data. They had better ability to know when things were changing, and we weren't going as long between tests too, so the track didn't have as much time to degrade as well in that time frame. So as you can see, as our testing has continued to gone up, our defect rates have gone down. Now we're at a point now where you can see we've been somewhat flat, and we've reached this point of maybe some diminishing returns where we need to assess long term, as we have the ability to do more testing now with locomotive systems, what is the right amount of testing to do? I mean, we could ramp up our testing. We're going to be over 500,000 miles of testing this year. With our locomotive systems, we have the opportunity to go well over 1 million miles and probably up to 5 million miles. But really, as a business, we need to understand, what is the right amount to do, because more testing may not lead to better results in the end. Because if it doesn't, then we have to ask us why we're doing it. And one thing I should mention too is that, I of course am an engineer by training. I went to school as an engineer. Most of you guys were here because most of us are engineers. But when you think about translating what we do to a business, right? BNSF is not an engineering company, right? No railroad is an engineering company. We don't exist to be engineers, right? We exist as a railroad. We're a transportation company. We are a business that makes money from moving goods from one location to another where their value increases, right? So that's what we operate as a business. We got to make sure as engineers, everything that we do, including this, adds value to the business in one way or another. And I talked about the value of derailment prevention earlier. Certainly that adds value to the business because our goods are making it to their destination more safely. Certainly that's value to the public that lives along our railroad. And then we need to look at the value of automated track inspection as well. So we're generating vast amounts of data, and what's the value to the business? So another example is automated track inspection. We do more track inspection by automated means, less by visual means. You think back before we even had geometry cars, every every type of track inspection was done just with human eyes and getting out and measuring with instruments and gauges and stopping on where you thought you have an issue, right? Everything, I would say 99.5% of all of our track conditions now from a track geometry standpoint are found with geometry cars like this versus a human finding it. So certainly there's advantages of finding those conditions through automated means. Certainly reduces the track time that's occupied for a human going out there and inspecting. It also reduces the risk to people being out there in a high rail truck and inspecting. And really, we send the people to where this system finds the defects. So that's the advantage of automated track inspection. And currently, I should mention too, we, BNSF, are the only railroad right now in the country to have a FRA waiver for automated track inspection. And right now that includes the Powder River Division, our Powder River Division coal loop. It includes the South Transcon and the North Transcon routes of ours. And that represents about 60% of our gross ton miles is covered by automated track inspection. So we certainly think this has shown, I mean, the results have shown that the track conditions have gotten better with more testing, and that we've been very effective in terms of reducing the number of derailments and the number of exceptions that we have geometry and track related through this program. And we're certainly looking to continue it further. But really, we wouldn't be here without all the data where we've come over the last 10 years of being able to generate all this data through our geometry cars and now our locomotive-based systems. I did want to talk a little bit more about Thor as well, and just show you a few more examples, getting back to Thor, on what Thor can find. So I think the biggest advantage, like I mentioned with Thor, is it's a optical system, and these are found via machine learning, right? There's not a person looking at the images, every single image, but once an image is pulled, our geometry desk will look at it to validate that it's a valid image. I would say generally our systems are pretty high in the 90 percentile range of finding these conditions. And then we have a validator making sure that it's correct, and we believe it's a condition to send somebody out there in the field to go correct it. Of course, I mentioned if we do see something like this, we are protecting it immediately as part of our geometry desk in Fort Worth. But the common safety critical items that we're finding with Thor are, I would say, fall into those 4 buckets there of broken rails. So that's a typical broken rail that's what that looks like right here. And I would say that this is the broken rail that really Thor adds the most value in finding. So those of you that may be familiar with the railroad, most broken rails, a broken rail like this is usually going to be found via our signal system, assuming it's signalized track. So any track we have that is either CTC or PTC has basically track circuits. So there's electrical current going through the rails. And anytime there's a break, the signal will turn red, or we'll get some sort of a track indication that says you have a discontinuity in that track circuit. So the majority of the broken rails like this, we have been finding fairly reliably for quite some time. These are the broken rails where Thor adds the most value, in my opinion, are the ones that are very challenging for the signal system to find. So you think about an electrical current going through the rail, this break occurs right on top of this plate. That electrical current is still going through that plate, and the signal system is essentially blind to that. So the best way of finding something like this is through Thor. A train will get over that, and there'll probably be a lot of trains that can make it over that. That break is well supported. It's not very wide. So there's probably a number of trains that can get through that. The goal is that Thor finds that before the wrong train goes over that break. And that's certainly what we want to find before it's too late. Other examples here, broken bars are a common one, broken components. And really this time of year is where Thor adds the most value. I mean, a really great example over this week. Big cold front has moved across the United States, and the coldest temperatures we've seen since way earlier this year we're experiencing this week. Excuse me, and that's when the railroad changes. That's when the rail starts pulling. Cold temperatures, rail wants to shorten, and the rail is going to be in severe tension, and the weak spots it's going to find it when the temperature drops. The other advantage of Thor, so I guess the biggest benefit of Thor, find those safety critical items that could potentially result in a derailment and find them before that happens. Second advantage is all the capital planning and analytics that goes with Thor. So those things that I just pointed out, we run something called models that are on the edge. So what that means is those models are running real time and are always looking for it. We also have several what we call cloud-based models. So Thor runs, and then all that information is uploaded to the cloud. And then there's models that run in the cloud, usually the next day or sometime shortly thereafter, that runs things that we want to know, but aren't necessarily like really urgent. And that reduces the amount of computing power that's needed physically with the system that's on the car at the time. And those are things like inventorying the railroad. Where are all your joints? Where are all your welds? What type of rail do you have there? Is your rail brand matching what type of rail we think is in the track? It's also finding potential switch conditions that aren't a concern right now, but could be a concern later on. And then the other thing too that Thor does, it's taking pictures of that track, and for every foot of track it goes down. So we can also do a virtual track walk from the office, basically. So once we run Thor, those gets uploaded into the cloud. Any of my team can go sit in the office right now, and if we have concern with a stretch of track that's on our Fort Worth sub, or Fort Worth sub wouldn't be a good example because that's close to the office, but somewhere in Washington, right? If we had a concern up there, we can pull up that track and just walk down the track virtually and look at the fasteners, the ties, the ballast condition without leaving the office. And that's something that certainly has come in handy with capital planning concerns. Maybe we've had an event and we want to look back and see what did the rail look like, what did the rail markings look like, what kind of work had been done there. So it's very, very valuable to be able to document and go back and look at the condition of the track without having to make a trip somewhere. So where does all this go? We've collected all this data I mentioned, whether it's track geometry, and there's all these other methods I haven't even gotten into too. We also have other ways we collect data. I mentioned GPR earlier, LiDAR, but most of what we use is track geometry related. But then how does that translate into actually the maintenance that we do and we plan as part of our capital planning processes here? So how that fits into our capital planning philosophy is, I'll share with you, is that we look at capital planning of a sense of, one, we want to maximize all of our assets, the life of our assets. And really that's one thing that all this data that we've collected now over the last 10 years has helped us to do better and better. Is you think about when you don't know how long an asset can live, and you don't know how quickly an asset is degrading, you really don't know when to replace it or how long you should be replacing it. And what we found was that we were replacing a lot of things on the railroad that had a lot of life left in them. Rail is a good example. Before we had geometry cars that were really giving us good rail wear data, we were replacing a lot of rail earlier than what we needed to, because it was based on somebody just going out there and measuring it by hand once a year and thinking that, well, yeah, it's about time to relay that rail, versus now this picture here on the right is an example of data we get off of our track geometry car. So every time a geometry car runs, we're getting rail wear data, and this is basically showing over time the rail is wearing, and eventually this is where we want to replace it. And we can see the trend of where that's going over time and know when to replace it. Before we had this data, we were just basing it off of field inspections and making frankly, a best guess. So that's one way we're using data to maximize the life of our assets. And that's just one example. Rails is an easy example because that's been probably the biggest one in the past few years. But also what that does is it helps us normalize our maintenance footprint. And what that really means is, if you look back over time, and I'm sure a lot of the railroads are very similar. If you look back over time, we've had years with lots of maintenance, and we've had years with very little maintenance. And we've had these huge swings of like, we go from replacing 4 million ties in one year to 2 million ties the next year, and then back to 3 million ties, and then back to 2. So it's been a very big swings of maintenance. And what we can do with all this data that we collect, whether it's rail or tie condition or ballast condition, is we can better forecast the life of these assets and better forecast what our maintenance footprint needs to be and smooth it out over time, because that leads to the third one, is workforce optimization. It's very difficult, as you can imagine, to ramp up a railroad when you have a very, very large railroad, to go from a very small maintenance program to a very large maintenance program in 1 year. That takes a lot of people to do all that work. And what we want is we want to have a consistent workforce that has about the same amount of maintenance each year, so we don't have these huge hiring swings. And then when you have a huge hiring swing and then you have a small maintenance program, that means furloughing a lot of people, which is what we don't want to do. So it's all about having a consistent maintenance process and making sure we're getting the life out of assets. You can see a lot of things on here feed into that, but those are the biggest highlights that I wanted to mention. And then getting into a little bit more detail of where our capital planning has come over the last 10 years. So that's, I would call that, I mentioned at the beginning, that's a really large part of what I do. I mean, track measurement feeds all the data we do, but in terms of building a $1.5 billion capital plan every year at BNSF, there's a lot of data that goes into that, and there's a lot of time and effort that goes into making sure we are spending that $1.5 billion in the right places and at the right time. And looking back over this time frame, I certainly can't cover everything, but you can think 10 years ago is when we started our tie scanning with the Aurora systems. Those are laser-based scans of our tie condition. So that's an example of data. That's not on our geometry cards yet, but we're certainly looking to get there here in the near future. So we have lots of data that comes in from our ties, and I'll mention that tie normalization is really the best example of smoothing out our maintenance footprint that I just described there. And if you look back in our history, ties is really something that we, prior to 2016, we really did not do a good job at normalizing all. We'd have these huge years and low years, and 2016 is when we called what we started tie normalization, where we on the railroad want to know, we know how many ties we have, we know the average tie life, so we should know every year we're going to put in about the same number of ties. It's just going to be spread out differently across the railroad, and that means we can have our sourcing team plan on purchasing the right number of ties every year. We know that's consistent. We are hiring, our manpower folks can hire the right amount of people every year. Our number of production gangs we have are consistent every year. And so that has led to really good benefits over time. And really, this is a good example here. As we have normalized our work, and I talked about earlier, what's the value to the business as a transportation business? What's the value to the business? Well, the value is, this is one example, is our system production gang count has gone from about 50 to a little bit less than 30 in the last 10 years. So you might think, well, you're doing less. Well, no, we're doing it more effectively with the people we have. We're doing it with fewer gangs. And a gang is basically a work group. For those of you that don't work with railroad, a gang is a work group that is occupying the track. And when they're occupying the track, trains aren't running. So we try and minimize that as much as possible. And you think of the value to our transportation partners and being able to serve our customers, having 30 gangs out there every day on the railroad, taking up time, not being able to run trains is much better than 50 gangs out there on the railroad, because that's capacity we have freed up over the last 10 years that we haven't had to build new track to offset. So good example of that. And then over that same time, you look at, well, is the railroad getting better or worse? The average daily floater miles has continued to decrease, and we've pretty much reached a little bit of a normalized level over the last few years. So that is another indicator to show us that, yes, we're doing it with fewer gangs, but ultimately the condition of the railroad has been improving over time because we're focusing our resources in the right place to where we really need it. So I'll cover here briefly on the bottom. I've mentioned a few of these already, but just the planning tools, the database tools that go into planning. So with rail, I mentioned all of our geometry cars generate rail wear data. So those lasers that are looking at gauge, surface, and alignment are also looking at the rail wear as the rail wears over time. Trains go through, especially in curves. You guys know the rail is forcing that train around the curve. So that rail is wearing away over time. And our geometry cars can see that and graph it like I showed you earlier. With ties, tie normalization, we know we scan our ties about every 2 years. We know the condition of how they're degrading, and we can predict that this section of track, the ties are gonna need to be replaced 5 years from now. And then after that, they're gonna need to be replaced 7 years from now. So we have that very, very dialed in very well. So the average tie life on our railroad is 33.4 years. And we know based on the number of ties we have on the railroad, we should be putting in about 2.5 million ties every year to keep that consistent. On the ballast side, I mentioned GPR, ground penetrating radar earlier. That combined with our geocard data, which gives us indicators of BFI as the ballast fouling index, which is one of the indices we get from GPR. That combined with TQR, which is track quality rating, which is an internal measure that we have for track quality. That those things feed into what we call our ballast model, and that's right up here on our capital planning history. Is our ballast model is one of the internal models that we have that takes all those factors in and determines where should we be high-speed surfacing, where should we be undercutting, where should we be track lifting, and it takes into account those different things because depending if the ballast fouling is really high. If the surface is poor, we know we need to do something. But if the ballast fouling index through our GPR is poor, we know we don't want to send a high-speed surfacing gang there because we're just going to surface it. The mud is still going to stay in the track. So you're just going to surface it up and waste a bunch of money servicing it, but the problem is still going to be in the track. So we know that needs to be either a track lifting or an undercutting program to really fix the problem. So that's how we're better utilizing data to not waste money in terms of production. And I would say in years past, before we had that, that might be an example of like maybe a location that had a high ballast fouling index. We probably would have sent a high-speed servicing crew there because we didn't have the data to tell us that was truly the root cause of the issue. And that would have been a waste of money because we would have done it and the problem would have come back and we just said, well, I guess we got to go do it again. But now we know what we truly need to do based on the data and the ballast model. And then I haven't mentioned this yet too, but we have a track reliability program as well that we track SIs or service interruptions. So anytime we have a service interruption, that can be of any cause, whether it's track related, signal related, anything that impacts service, we track that of location, milepost, subdivision, what the cause was, and we use that data to also plan our track capital to the right spots, meaning a location with a high frequency of service interruptions, meaning there's a service interruption, usually it means a switch can't throw, there's a broken component, something going on there. We know we need to direct more capital to where the service interruption rates are higher than others. So that's another way we're using data as well. I mentioned this already, but I just want to share, this is an example of the case study of our maintenance footprint and all the normalized maintenance I talk about. You can kind of read some of this for yourself, but pre-2015, you can see this is what normalized maintenance and database maintenance does for a railroad and a business in terms of the value that we add to it as a transportation company. I mean, prior to all the data that we were collecting, you can see our average daily slow order minutes are now in half after that. Capital maintenance miles significantly reduced because we're normalizing our maintenance, we're spreading it out, we're making sure it's in the right spots. Number of gang windows every day significantly reduced, almost cut in half. And as I mentioned earlier, the number of physical capital gangs out there on the track are almost nearly cut in half. And as you saw in the earlier slide, our metrics have continued to improve over that time. as well. So the data that all feeds into this has really allowed us to get really, really good at planning where we need to do the work and by when. So the last thing I wanted to mention, certainly I've covered a lot already, but I wanted to mention this because we're really proud of it at BNSF is, and it's one of the bigger problems that all railroads need to solve is track buckle prevention. I think we all know the general climate of the U.S. has been getting warmer. We've been seeing warmer summers. Our rates of track buckles, meaning when the track gets hot, it wants to, we have a high rate of compression in the track because the rail wants to expand, and it leads to potentially a track buckle. But one of the studies we've been doing is around rail temperature prediction. So we've developed our own rail temperature prediction model within BNSF. So very proud of the team for doing that. That's been a collaboration between my team in engineering as well as our BNSF tech team and TR&D. So you can see a common theme here. We collaborate well between our technical research department, our technology and engineering to all come up with these in-house solutions. But this rail temperature prediction model, I think, is just, it's been around for about a year or two so far, but it's really unlocked a lot of things we want to do around track buckle prevention. And I'll give you a few examples. You can see for yourself on how we predict the rail temperature, but it's way more in depth than just saying rail temperature is 30 degrees warmer than the ambient temperature, which has always been a rule of thumb of railroaders, that if it's 70 degrees outside, your rail temperature is probably 100 degrees. This is really taking into account the weather forecast, the actual weather stations we have out there on the railroad, angle of the sun and solar radiation and cloud cover and all that stuff. So we're really getting good rail temperature prediction. But what that really allows us to do is we have, and the number of models that this feeds into is growing every day. But the things, I'll give you a few examples of what we're doing with it, is we have heat inspection models. So it's basically a track buckle risk model, for lack of a better term. If we map the railroad and we identify hot spots and where we have the highest risk of a potential rail buckle out there, that's feeding into that. And we direct our inspectors to go monitor those locations more closely on hot days. But the other things that I think it has the most value in is through our automated compaction processes. So I'll give you an example of two of these. One we've had around for about 5 years now is our compaction process. So typical process for any of you that worked on a railroad, whenever we disturb the track, so whenever we do maintenance, we put on a compaction slow order. So whenever you do maintenance on the track, that it reduces the lateral resistance of the track. So the track is weaker after you do maintenance. So the way we compensate for that is we slow the trains down. The trains go slower for some period of time until the tonnage raises the strength of the track back up. So we do that in an automated fashion now. So whenever our teams do work, they put on an order, a compaction order that they place out there. And then our systems in the background monitor how many trains are going over that, what's the tonnage of each individual train, it's adding the tonnage up. And depending on the temperature, the forecasted rail temperature, it determines automatically when to remove that compaction order. So no one has to be out there. It could be the next day in the morning when it gets removed. But we're automatically removing those compaction slow orders and bringing the trains back up to normal speed when we've had the right amount of tonnage. Now, we've been doing that for about 5 years, but the basis of that is all rail temperature prediction. But one of the new processes we've had this year, which is brand new, was what we call our heat focused compaction model. So what we found in years past is that track buckles that happen are generally are places we've disturbed the track, but not necessarily places where we've disturbed the track yesterday or the day before. It's often places we've disturbed the track a month ago, or maybe even 2 months ago, where we've been running trains at full speed for a while, but the track still has not reached its full strength yet. So what we've added a new process called our heat focused compaction slow this year that uses this data and basically says, it looks at where have you disturbed the track recently, where have we not gotten 1 million gross tons over it? So it's a much larger tonnage than a normal compaction look back. And it says on a really hot day, like if it's going to be 95 degrees today, we're going to put a sloater on that track between the hours of 2 p.m. and 8 p.m. during the hottest part of the day to reduce the potential risk of a track buckle by slowing the trains down, reducing the forces into that track, because we know that track still has not gotten back to full strength. It's still okay under normal conditions, but when it gets really hot, the hottest part of the day, from 2 to 8, we're slowing those trains down. So we've run that this year for the first time. It's all an automated process. So that was a new development we had this year. But I would say that's an example of the doors just cracked open a little bit. But the future of where this goes is just looking at the more data we can collect, whether it's weather and train data. I think this is the future of where all railroads can go, is really being surgical on protecting the track where it needs to be protected, and potentially even for the specific trains it needs to be protected for that have the highest risk for something happening, whether it's a buckle or a rail break or something like that, because this has applicability. You know, we're talking about hot temperatures here. I think this has applicability on the cold temperature side too, where trains that have the highest risk of maybe causing a broken rail based on flat wheel conditions or wheel impact conditions as well. So I think the doors cracked open. I think this is a good example of that, but I think there's a lot of potential for us to get really good at predicting where a failure might occur with a specific train, and then adjusting the speeds and the conditions to make sure that we're increasing the factor of safety to avoid a potential incident. And ultimately, that's how we're going to get to zero track-related events eventually. And hopefully, I get to see that in my career. But we keep on our steady path to get there. So that's all I had. Those are the high points of database maintenance at BNSF. And now I think we'll open it up to really any questions that are out there from the audience.
First of all, that was excellent. How about some questions from the room, and then we'll filter in some questions from the online audience.
Yeah, if you go back to slide 12.
Slide 12.
There you go.
Yeah.
In the upper right corner, it looks like there's a wire attached across that brake.
Yep.
Is there a reason for that?
I believe that's probably a bond wire for one reason or another. I didn't know the exact. I wasn't sure the exact location of this picture, but
Yeah.
there must have been a bond wire there for one reason or
It
another.
looked like there was a joint where you'd expect to see a bond wire. It's kind of wondering.
Yeah, there might be something off to the right. There might be something off to the right that we can't see, but that's a good question, though. I'm not sure. But another good reason why we need Thor to find that too, because you got another path for current to go around the brake.
So you mentioned all your technology is in-house, but you're also not an engineering company, obviously.
Yep.
So would you consider have you sold this technology to other companies to use in their products?
Yeah, we have not, mainly because that's not our core business. I would say is the potential there at some point in the future, but maybe. But to this point, we haven't pursued that.
Makes sense.
It's not really our wheelhouse. We're good at developing things for us, but not commercially at this point. Yeah.
Great presentation. Very, very informative. I've got a million questions, but I'll ask one. In one of your slides, you mentioned the tools that you're using for each rail, ballast, and so forth. And I noticed under rail, you have track modulus listed.
Mhm.
Is that something that BNSF measures, tracks? How is that considered, or how's that data gathered for using that in those models?
So we're just in the infancy stages of being able to use track modulus. I would say at this point where it's not regularly used, but given the fact that we have locomotives now, geometry systems on locomotives, plus geometry systems on cars, we're trying to get a better, see if we can better measure track modulus is where we're at right now. So I would say yeah, being able to compare what does a track look like under a locomotive versus a car, and trying to be able to calculate a track modulus or stiffness, right? So I would say we're in the infancy stages of that right now, but it's something that's part of our development.
So I'll give a few online questions here to you. First one about Odin. Do you intentionally schedule the locomotives that have the Odin system on it on specific trains to maximize coverage, and how do you work with transportation?
Yeah, so we do as much as we can. One of the unlike our attended geometry, or unlike our geometry cars where we schedule them to where they specifically can go, we try to schedule Odin on the right locomotives, but the reason we're planning on having 65 Odin systems versus 4 geometry systems is we don't have control over the locomotives, and really it's more of a, we're trying to go for just saturation, to making sure that if we have 65, we are covering the majority of the railroad with those. Also knowing that some of those will go offline, some of those will go into the shop, and there's going to be some other reasons that locomotives will go different routing. So we have tried just not really, we have been reasonable to expect that we're probably not going to be able to control where the locomotives go.
About a Thor question. So in terms of number of defects that you actually detect in the field, how often do you actually capture one on Thor? And in terms of false positives and accuracy of the algorithms that are the defects, do you make any comment?
Yeah, I don't have the exact number on hand right now, but we do have a false positive rate with Thor. It's pretty small, but generally that's why we have the overlay of the track geometry desk, because they are finding false positives at the desk, and obviously if they see something as a false positive, then they're not going to send it out to the field, because we would rather have the desk find it than have someone in the field go out there for no reason and tell us that it's not there. But it's a fairly small percentage.
But one more from the online audience. There's a lot of questions about the technologies, especially the 2 that you've highlighted you developed in-house.
Yep.
I'm going to summarize one of the themes relates to how did BNSF make the decision to develop these technologies in-house versus using other commercial systems?
Yeah, I think overall you're right. I mean, we had the option that we could go purchase a system. There were several reasons. One of which was cost. We felt we could do it cheaper than purchasing from externally. But the other thing is, I think more so we wanted to have control over what the data was. I think some of the concerns we have with systems, especially when you have it from multiple vendors, is there's a bit of a black box in everything a lot of times when it comes to calculating track geometry, or even other systems. Is we wanted to have consistency of knowing what went into the calculations, what's going into there, so we knew the output was correct. Not to say that other systems aren't correct, but I think we wanted to have more control over knowing that our data was correct, and that it was matching the things that we wanted to test for, and that we were part of it from start to finish. Is really the biggest reason.
Great presentation. Thank you so much. I learned a lot. A quick question on Orton and Thor systems. One is locomotive based, another one is geometry car based. Can you elaborate more about their separate purposes, like which one is for what? I know for Thor, you went into details. You use computer visions to detect the broken tracks, something like that. What about Orton? What's the difference between these two? And then which one is edge computed, like it's processed on locomotive,
Yep.
or you need to send data to a back-end cloud where you basically do all the labeling.
Yeah, so Odin, as of right now, Odin is just a track geometry system. So it's only measuring, it's a laser-based track geometry system. So it's only measuring gauge, surface, and alignment of the track. And it does that all on the edge. It sends it to our track geometry desk in Fort Worth. So it's not taking pictures of the track. So it's just laser based. It's doing basic track geometry measurements. Thor is the optical image based system. So that currently is only on a geometry car platform. We do have plans to put it on a locomotive. We just don't have it right at this moment yet, because an image based system just requires a lot more computing power, especially on the edge. When you're taking images, the amount of data you're generating. I didn't really get into these. This is another thing with having a lot of data, is the amount of data you're collecting just grows astronomically with images compared to just data. When you take track geometry, you're just taking measurements, right? Numbers over time. Whereas you're taking images, that's a lot more data, and you start adding that up over thousands of miles of track, and that's a lot of information to get transmitted off of the car somewhere else, and also to be able to store it all. So Thor is an image-based system. So you're taking pictures. So everything from Thor is you're visually looking at something, and the machine is telling you if it's something wrong. So Thor doesn't take any measurements. So it's really, you're looking for two different things. It's geometry, you're looking at the condition of the track, the geometry of the track, and Thor, you're physically looking at the condition of the track. And then if it's really, it's like, are any components missing is really the biggest thing I could describe it as what Thor does. Now, like I mentioned, we want to have both on a locomotive at some point. We're just in the development stages of getting Thor onto a locomotive also.
Great, that's an excellent point. Thanks very much. A very small follow-up question is, how do you distinguish the ordering system on locomotive versus a just traditional geometry car, where you also measure the track geometries, like for example in the Harrier cars and like that? How do you distinguish these two? Like which one?
In terms of which we use it for, or what?
Yeah, pretty much.
Well, so Odin is new. So we started with geometry cars because that was the easiest solution back when we started. But Odin, we wanted to get to a point where we could do it on a locomotive in revenue service. So it's invisible to transportation. Because right now, a geometry car that's out there running around is another train that we've added to the network that is not generating any revenue for us. So we wanted to make it invisible so that it was on a locomotive. And we weren't sure how big we wanted to scale it up too, because if we could look at putting it on lots more locomotives if we wanted to. But that's really the transition we went to, is trying to move more towards a separate car-based system to getting it onto a locomotive now.
It's really integrating geometry cars into locomotives.
Yes, it's basically doing what a geometry car does on a locomotive. Now, the reason it wasn't done, I mean, you think about a locomotive does a lot of other things, and there's a lot of other components and systems on a locomotive. The challenge was just finding the space on the locomotive to put the system so that it's reliable. Because the easy part about putting it on a car is you have a car, you can put stuff wherever you want. You can put it, there's room for servers and data, a lot of communication devices to get on a car. Locomotive, it's a lot more difficult. There's not that much space on there. So that's why it was a little bit more difficult to get on there. And that's why we did cars first. But now that we've solved locomotives, and as we get to Thor, computing power gets smaller and smaller and smaller and smaller. That's really going to help us get Thor onto locomotives as well. And that's really what helped us get Odin onto locomotives. Computing power got even better over time. That now the CPU for the Odin is in that box that was up there. The CPU is in a box that's this big. Whereas 10 years ago, that same box, the same computing power was probably, 10, 20 times as big back then.
Last question.
Good afternoon. Great presentation, really informative, very interesting. What I'd like to ask is, you guys develop a lot in-house, and something that we've been hearing a lot lately and probably will still be growing is the hype of AI. So how do you guys foresee the use of AI in your detection systems or post-processing, or with all those different equipments? How is the vision for that within BNSF?
Yeah, I think it's true. I mentioned too with the data quality. So I think that's the first thing that comes to mind is, the data quality that comes in off of these systems operating in the real world is never going to be perfect. I mean, we're not going to get rid of the snow and the sun and all the different elements that cause issues, dust in the desert. So I think it's AI is being able to do more of finding those when we have an issue, and either turns off the system, ignores it, and it gets smarter about getting us better data quality. So a person doesn't have to look at that and say, oh, that's no good. Whereas AI is doing that on the front end. So, and I think it'll eventually that'll get to less handling from our geometry desk over time. Because right now we have the geometry desk set up with a person there as a last line of defense before it goes out to the field. I see the more AI tools we have, the less we need somebody on the back end validating it to make sure it goes out to the field. So whether that's data quality or it's even just making sure, like we mentioned, the false positive rate, while it is small, is the reason we have people there to make sure we don't send someone out. But I think if we get that false positive rate on identification of issues to virtually zero through better artificial tools, that gives us more reliability to say, well, nobody really needs to look at this before it gets sent out to the field. And I think those are the big things, is just less human intervention before it gets out there. And then, two, I think if we get really confident with everything that's sending, I think it's just not having a human in the process to be a final validator is probably the biggest thing I can think of to summarize if that answers your question.
Yeah, thank you so much.
Yep.
That was tremendous. Really great questions, tremendous responses. And actually in that last question, you fielded several of the questions that came from the online audience. There are many more from the online group, but we need to wrap this up in the interest of time. How about one more round of applause for Todd? Small token of our appreciation, we have both a mug for you that celebrates our 25th anniversary.
All right.
Some of the faces that are represented in the small images there are now employees at BNSF.
Oh, great.
That's exciting. And then
Thank
a
you.
coaster as well, a Realtek coaster. So thanks again.
Thank you very much. Thanks for the input.
Good rest of the day and weekend. Thanks for coming.